Well, good morning, everybody. 6:58. I think we'll wait till 7:05 for people to come in. Uh, what did we learn last week? Okay. In fact, I kind of dealt with last week pretty terribly, so I'm just going to bring up the thing from last week. Algorithms 3. I'm just going to bring up the thing from last week so we can go over it quickly, just that everything is properly in order. Oh yes, also, good morning. Why do we only have 5 people? Because it is currently 6:59. Hopefully there will be more. Hopefully. There might not be, which would be very disappointing. But algorithms and theoretical computer science, we were discussing searching and sorting algorithms. So searching is, according to Google, when you look for stuff. For example, these are things that people tend to lose: keys, children, TV remotes. And when you lose them, you got to search for them. Admit this person. Good morning. See, we're already up to 7. So searching is when you do that. Just going through this real quick. Linear search is a way to, if you have a bunch of items and you want to find a specific item in that collection, well, yes, you do occasionally lose children. It's unfortunate, but it happens. I've done it. It's no shame. So you go through the collection one element by one element, and you just check, is this the right element? No. Okay, next one. Is it right? No. Next one. Is it right? Yes. Okay, great. You've got your element and you found its position. So that's what you do when you try to find the position of an element in a collection. For example, in the previous example of children, you have a bunch of children lined up. You want to find your child because you've gotten them lost again. Pesky children. You go through one by one. Is this my kid? No. Is this my kid? No. Is this my kid? No. Is this my kid? Yes. Great. Easy. However, this is only when they're randomly assorted. When your children are all lined up, say in height order or in name order or whatever, and you know the height or name or whatever of your child, then it can be easier. You can do binary search, which is where you divide up the search space, the row of children, bit by bit. So for example, you could look at the middle and go, okay, is this kid taller than my kid? Yes, he is. Okay, so I don't need to look at anyone who's taller than him. So I just need to look at all the kids shorter than him. And because they're lined up, that's all the kids to like the left or right of him. Yes, indeed. So yeah, or if they're alphabetized and you're looking for Joe and you find, I don't know, John, then obviously John comes after Joe in the alphabet. So you know you're going to have to look before John, and you can just immediately rule out all the kids who come after John in the line. So it's useful. You divide it up one by one by one, and this is a divide and conquer paradigm. Why I'm not actually doing any code for it, because it's difficult, basically, TLDR. Sorting, on the other hand, is when you, well, as we discussed, if you want to run binary search, you're going to have sorted data. You can't just have data in random order. So if you want to sort stuff, you're going to have to arrange it into the prescribed sequence, and we have algorithms to do that as well. And the only one we discussed was bubble sort. I'm going to move this, it's in the way, which is as long as the list is not sorted, you go through pair by pair by pair by pair. If they're out of order, you swap them, and you just keep going. And we ran through a couple examples of that. Good morning. People are stacking up. We've reached double digits, I think. Yeah, we've reached almost double digits. Anyway, yeah, that's bubble sort. And this is also a greedy algorithm. You're moving through, and at each point, you're making the optimal decision of, okay, these guys are out of order. Let's make them in order. And that's an optimal decision at the local level. And it actually does add up to a globally sorted list. Where am I when it is morning? Right now, New Zealand. It is not morning. I don't know why I said it was morning, but yes. In any case, also if you didn't see that, I just saw my camera bounce up and down. I was looking out the window. Anyway, bubble sort, and then we took a short detour into big O notation, a very useful concept, in which we discussed how some algorithms are better than other algorithms. For example, binary search is better than linear search, but it needs the list to be sorted first. Or bubble sort is worse than quick sort, which is one we didn't discuss. It's called quick sort because it's quick and it's high performance. And what we discussed was we're trying to minimize number of operations. We discussed the average case, so algorithms don't always work the same for some input data, and one algorithm will do well and another will do poorly. For other input data, the second algorithm will do well and the first algorithm will do poorly. And you just want to deal with like randomly sorted data, average data. And finally, we dealt with Big O and this terrible Obama meme. And Big O notation is basically just a fancy mathematical way of describing how many operations an algorithm will take based on the size of the input, which is called n typically. So here we had some exercise. We did some exercise. It was great. did some linear, we classified them as ON, O-login, and ON squared, and that was all we did. And we did not do this terrible thing with the sonic mean because I could not bring myself to do that. Now, so much for that. Can I escape this? Am I allowed to exit full screen? There we go. So much for that. It is 7:04. We probably got enough people. 9 people is good. Scared some people off by poorly handling last week. Sorry about that, guys. Very, very sad. Tried to pack too many algorithms in. Didn't work. This week we've only got 2 algorithms to deal with. I think, yeah, 2 algorithms to deal with, so it should be fine. So with no further ado, let's get started. So this week we're dealing with graph algorithms. Now, that was horrible pronunciation, graph algorithms. Now, who's heard of a graph? Just raise hands. Where's the participants list? Here's the participants list. Raise your hand if you've heard of a graph. We have 1 raised hand, 2 raised hands, and a thumbs up. That's pretty snazzy. 3 raised hands. Okay, a lot of people have heard of graphs. That is good. That is good to hear. However, the question is now, what type of graph are we talking about? Are we talking about, for example, this thing here, which, are we talking about these kind of things here, which it has a big X over it, but if you can make it out under the X, it's a graph of a function, which goes like this, up and down, and it's got some axes. Are we talking about that kind of graph? A lot of people will probably have heard of that type of graph, but amazingly enough, there is a different definition, and that's what we're going to cover today. So who's heard of graph theory? We'll type that in. Graph theory. Because for some reason, mathematicians are like awful at choosing names. Mathematicians and physicists, it goes for all of them. They're terrible at choosing names for things. Like, you have already named something a graph. Like, when you depict things on axes as like relationships, that's a graph. Then they went and made this other thing called graph theory. So who's heard of graph theory? Because graph theory is entirely different, and that's what we're going to be discussing today. Music theory is cool, but it is unfortunately not graph theory. Okay, so what graph theory is the study of these certain mathematical things called graphs. And here's the very overlong Wikipedia definition, but TLDR, a graph is a thing which models relationships between things, which may sound confusing, so let's give an example. Very nice photo of air travel. I think that might be Cambodia, I'm not sure. So, if you were a frequent air flyer, I don't know, you might go, okay, some airports, you can have a direct flight between those airports, and other ones you got to go around. You got to go like a long round trip. For example, if you want to get from LAX to New Zealand, I don't believe that there's a straight flight from LAX to Christchurch, where I am now. I recently went there, and the way you got to do it is you go from LAX to like Fiji, and then down to Auckland, and then down to Christchurch, which is where I am now. So that's a lot of stops. And unfortunately, there's no just direct LAX to Christchurch. So the question is, how? Hey, Christchurch. Christchurch is a great city. Yeah, that's Christchurch out there. So the question is, how can we record that information? Is there an easy way to like write that up instead of just writing down like a big table saying, oh yes, Auckland connects to Fiji but doesn't connect to LAX. LAX connects to basically everywhere, that kind of stuff. Is there an easy way we could write it up, like a diagram, something like that? Can anyone think of a way we could do that? Feel free to just unmute, by the way, and just say it loud, because typing takes a while, and speaking takes much less time. A graph. Huge brain. Yes, that is correct. I'm not sure if I should give points for that, because that is like the thing that we discussed on the previous slide, but yes, you're absolutely correct. We use a graph. And so, here we have a graph depicted. So, we're going to use this lovely little paint tool, which I am so poor at using. Sorry about that, guys. So the way we draw a graph is we draw these little circles. And these circles represent objects. For example, this could be Auckland. I don't know, AKL. I'm not going to draw all the airports here. That would take way too much time, but this can be Auckland. It could be LA. LAX. And this down here could be, I don't know, Fiji Airport. I don't remember which ones that's called. I don't remember the exact code, so I'll just call it Fiji. So the little circles are called nodes, and they represent the things. And now, the way we represent a relationship between things, say this thing can connect via flight to this thing, is with lines. So Auckland does not connect to LAX, but LAX connects to Fiji. Whoopsie daisies, it was horrible. and Fiji connects to Auckland. Yeah, that's a little better. You don't typically draw the lines over the nodes, but yeah. The lines are called edges, like the edge of a knife, and the nodes are called nodes, and there's no real analog for that, but analogy for that. But so this is how you would depict it. And if you wanted to add another node, say New York, I believe that New York NYC, I believe that Auckland just opened up a cool new program where Auckland you can fly direct to New York, which is pretty cool. And obviously LAX to New York you can go because they're like the biggest airports in the world. Fiji you can also go to New York. So if you wanted, you could probably do a much speedier flight if you wanted to get from LAX to Auckland. Instead of going to, I mean, yeah, from LAX to Auckland, you go LAX Fiji, Auckland, or you could go LAX NYC, Auckland. But just geographically, LAX Fiji, Auckland makes more sense. It takes less time. But if we're just recording relationships, this is how you would record them, with a graph. Yes, I'm not an artist. I am a computer scientist. They don't tend to have much overlap. So that is how you would depict it. Now, so this is just the terminology and another picture of an airport lounge. So in this case, the airport itself is the node, and like the flight between two airports is an edge. It's all about representing things and connections. And graphs are pretty cool. So graphs can be used for, here's a stock photo of bullying, and here's a stock photo of a house layout. So basically, legitimately anything that involves pairwise relationships between things. And I know that I don't tend to give you any homework because I told you I would unequivocally not do that, but just as an exercise, if you're walking down the street and you see like a thing, like try to think, can this thing be interpreted as a graph? Because a lot of things can be interpreted as graphs, like roadmaps, for example. So the way we would lay out this, the way we would turn a house layout, by the way, Alt tab, where's my Alt tab? Here we go. Okay, the way we would turn a house layout into a graph is, I'm going to use my epic eraser. Oh God, file new, don't save. That was terrible. We are not saving that. So, let's say, for example, we want to turn this house layout into a graph. The way we would do that is, and this time I'm just going to use text instead of little circles. I'm going to make this bedroom, bathroom, another bedroom over here for some reason, kitchen, dining room. They don't have to be geographically accurate. I could put the living room all the way over here, for example, and then we'll have also the porch up here. So the way we would do this is by drawing in lines, and they even have a line tool. How cool. So for example, the porch you can only get to from the living room, so we would draw a line between them. The living room you can only get to from the dining room, so we'd draw that line between them as well, and the kitchen you can only get to from the dining room, we'd draw a line there too. From the dining room, you can get to like this middle space. In fact, I'll just add a little thing for the middle space. This little area here. From the dining room, you can get there, so like this. And from the middle space, you can go to all three of the bedroom and the other bedroom, wiggle around here, and the bathroom. And that pretty much incorporates this house as a graph. What we lose in distances and actual layout, we gain, yes, streety things on maps in the movies, exactly. That just depicts like relationships. Midspace is carrying, and indeed we could talk about the degree of a node being like the number of edges that come out of it. And in this case, midspace is absolutely carrying because it's got the biggest degree. Dining room comes second with 3, but midspace has 4, and so it's definitely the one with the highest degree. All the others have either 1 or 2. Most of them have 1, like porch and kitchen. Some have 2, like living room, and those living room ones are kind of like in-betweens. They're serving to connect dining to porch, for example. And how is bullying related to that? Well, file, new file. Let's depict, don't save, obviously. Let's depict this network. So we're going to have some kids. We're going to call them A, B, C, that was on the C, D, and E. Left to right, A, B, C, D, E. It appears that A is friends with B, so we're going to draw a line there. And it also appears that that D is friends with E, so we're going to draw a line there. And C is being bullied, so C has no friends. And so, like, and maybe A, D, and B and E are also friends and they form like a clique or something. Very unfortunate. High school dynamics are just very unfortunate. But yeah, That's how bullying is related to house layouts. You can depict them both as a graph. And this graph, who's seen this graph before? Because this graph is crazy. A tree graph. We're going, and I think that that's the next slide. So yeah, you're ahead of your time. So who's seen this graph before? I'm blocking it off. It's insanely complicated graph here. At first, it just looks like a tree graph, but I believe there are cycles in here, so it's not a tree. So a cycle is when you can go from one to another to another to another and get back where you started, and like cycling around. This graph is the graph of the internet. All of these little dots are web pages. The ones with a lot of lines coming out of them, and lines are links between web pages. The ones with a lot of lines coming out of them, like this one here, for example, is probably Google or something like that. One that relates to basically everything. The ones with fewer lines coming out of them, like these little sad ones over here, are probably like my special web page, which I made as a high school project in 2011, and like don't do anything, and they're only linked to like a couple websites. So yeah, this is a map of the internet. Pretty cool, and it's probably the most famous graph in existence today. Next up, premonitions, tree graphs. They're not trees, unfortunately. They're graphs which don't have any cycles in them. So a cycle is, so this is actually factually wrong. You can't go from LAX to Auckland, but whatever, I think. But whatever, we're just saying that you could, for the purpose of this, you can go Auckland, New York City, LAX, Auckland. And you'll notice that in this graph below, where the circles are the nodes and the lines are the edges, there are no cycles. You can't start at this node, say, get out of here. You can't start at this node and go to this node, this node, this node, somewhere else, and somehow get back to this node without covering any distance that you've already covered. You go like down here and then come right back up, but like that's cheating. You can't do that. A cycle is when you go around and you don't visit anything you visited before, and you somehow end up back where you started. And a tree is a graph which doesn't have any of those. And trees are super useful, as we're going to find out. Maths questions, yeah. Trees are a very common concept in math. They're probably the graph that you deal with most in math. But there are other types of graphs, of course, like graphs with cycles, for example. So, anyway, queues and stacks. These are somewhat ungraph related, but I'm going to discuss them anyway because they're useful in graph algorithms. And then we are going to get right into the cool stuff. This is 7:16, but thankfully we've only got 2 algorithms to cover today, so the cool stuff will not take long. Can't speak today. So queues and stacks. Queues and stacks are like there's structures in which we hold data. You can imagine like buckets in which you put your data, and they hold data differently. So in a computer, you can't just say, "Oh yes, take all this data and put it in a lump over here," because computers don't really understand like put it all in a lump over here. They've got to like put it in their memory and index it and do like have a location for all the data and like line it up. So they need structures, and more importantly, they need to know how to put things in and how to take things out of your data structure. So a queue is like a real life queue. When you put a piece of data in, it comes in at the back. And when you take a piece of data out, you take it out of the front over here. So like a queue, you line up, first guy in is also the first guy out. So it's called FIFO, which stands for first in, first out. However, this is not the only possible data structure. Second possible data structure is a pancake stack. Let me move this. Pancakes are delicious. I haven't had any pancakes in a while. I should change that. Anyway, pancakes. The idea of pancakes is you cook a pancake and you put it on the plate, and then you cook another pancake, you put it on the plate. Which kind of awful person is going to ask for the pancake on the bottom? No one. No one's going to ask for the pancake on the bottom. They just want the pancake off the top. So the idea of a stack is that the thing that got put on last is the first one out. So last in, first out, LIFO. And FIFO and LIFO, call centers, yes, in a call center, the data structure will typically be a queue. And many people have wished to God that it was a stack. Because if you're calling a call center and you're like, oh, hey, can we come in? They're like, oh, we'll put you in a queue. When we get to you, we'll get to you. And you wish, I wish because I was the last in, I wish I could also be the first out, the first guy to get dealt with. But unfortunately, the first guy to get dealt with is the first guy to come in. You just got to wait your turn, which is unfortunate. So yeah, those are 2 structures. Get out of here. Get out of here. Those are 2 structures, and yeah. two structures in which we can hold data. Stacks we will use later, queues we use right away. So, got a question for you now. In this one, we're going to actually try and make an algorithm ourselves. So I'm going to ask you guys, if you wanted to find a path between, say I gave you a graph of all the airports and which ones can go to which ones, and you don't care about travel time, you just care about like not going to too many airports, because the more airports you go to, the more likely it is that your luggage gets lost, and you don't want that. So you're like, okay, how am I going to find the path in this graph that visits the least nodes? In other words, the path that goes to the fewest airports. For example, I chose Azerbaijan because this is such a cool photo. Like, look at this city. Who wouldn't want to live in this city? That's cool architecture. So this is Baku in Azerbaijan, this photo here. And if you wanted to get from Auckland to Baku, you would have to go, according to Google at least, you have to go to Adelaide, and then you have to go to Doha in Qatar, and then you have to go to Baku in Azerbaijan. And that is the shortest possible path. You can't go in fewer stop-offs. There's no Auckland to Baku direct flight, or even an Auckland to somewhere to Baku direct flight. Like Auckland, Singapore, Baku, that's not a real flight. They don't connect up. It's very sad. So a question for you all is, how do we find the shortest path? If I give you a graph, how do I find the shortest path? Bring up the chat. Anyone who wants to unmute with a proposal of an algorithm, feel free to. I'll give you like a minute. Just think about it. Drink some water. If only. If only we could connect them all. But so I assume what you're saying is like just make a flight between Auckland and Baku, and if only we could do that, that would be great. But unfortunately, if we got to work with what we got, like only the flight plans that we've got, and we can't add new edges to the graph, how then could we find the shortest path? If connect all the ones and select the least amount of nodes passed.
Okay,
Not sure I understand.
that makes like no sense, but basically like program it so it goes through the one that passes through the least amount of nodes.
Kind of like the Warnsdorf's night tour algorithm from last time, or I can't quite understand what you're saying, but it sounds smart, so I'll give it a thumbs up for that one. Also, I've noticed that so far, approximately not approximately, two people have talked. So let's see if someone else can talk, because as I last checked, we have 9 participants. I remember when we had 20. Very sad. I suppose some of them have gotten lost along the way, but that is fine. Of the 9 participants, I count via quick math that there are 7 of you who are not talking. So if you're among that 7, step forward, and if you've got an idea, go for it. But actually, in the interests of we're already at 7:22, and I think we'll do it all in plenty of time to spare, but still, I don't want to run out of time like I did last time. That was very unfortunate. So we'll not allow that to happen. We will just deal with the shortest path algorithm right away. So this is a lot of text on the screen, so we're just going to work through it bit by bit. And the way we're going to work through it is by first I'm just going to show you on a paint thing. Delete this. So let's see. With first search, we're going to just make a quick graph. Say, have a bunch of little circles. The sizes don't matter. I'm just quickly dragging them. Now we're going to have a lot of lines, edges connecting them. This graph is currently a tree, but I'm going to make it not a tree by adding another edge here. Like, no, not that edge. I'm going to add another edge here, make it not a tree. So now we have a cycle that goes here, 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 and back here. So this is a cycle, a loop, if you will. So in this graph, we're going to perform what's called a breadth first search. It is a very connected graph. So the way that a breadth first search works is we start at a node, and I'm going to say, just for the sake of why not, we're going to start at this node here. Excellently colored in. And we're going to try and terminate at this node over here, I think. Is that a good node? Yeah, that's a great node. And try and terminate at this node over here. So we're trying to find the shortest path between these two. And just intuitively, we can see that 1, 2, 3 is better than 1, 2, 3, 4, and is definitely better than like 1, 2, 3, 4, 5, 6, 7. So like we can already see that the shortest path is probably going to be this. But this is how breadth first search works. So we create a queue, and my queue is going to be down here once I can get some text box. Okay, so the queue consists of all the nodes we haven't yet visited. And in fact, I will give them names real quick, just to make it nice and easy. 1, 2, 3, 4. I'll give all the nodes names, number names. So we're trying to get from node 2 to node 8. I can change the size of the brush. That is a very smart idea. I'm going to do that. Thank you. Size. I'm blind. Size. Wait. Oh, yeah. Oh, now we're talking. Thank you so much. Okay. Yes, the names they aren't much, but honest work. So we're going to start at 2 and we're going to get to 8. Now, the way it works is we start by adding stuff to the queue. So the first thing in the queue is just 2. We start with the start node in the queue. And now we repeat a certain step. And in this step, we take the last node from the queue and we pop it out. So what we've just added in, 2, and I'm just going to remove again. Great fun. And we pop it out and we look at it. So the node we've just popped out is 2. The question is, what do we do with this? We find all of the nodes that are adjacent to 2, so that have edges connecting them. So that's node 1 and node 5. They're the ones that are connected to 2. So once we have them, well, the algorithm is listed here. We find all the adjacent nodes to it that haven't yet been visited. And yes, sorry, I should also make another little thing, which is called visited. And I can't spell. Visited, in which we will record all the nodes we have visited so far. And right now, that is just 2. So the way we do it, we start with visited and the queue, both containing 2, and then we move along. And by the way, a queue is, when I say queue, I mean like this queue data structure. So first in, first out. So we've got node 2 and we're considering node 2. The adjacent nodes are 1 and 5. So what we do is we visit them both and we add them both to the queue. 1 and 5. Visited is 2, 1, and 5. And once we have done that, we highlight the edges between them. Here's my brush. Once we've done that, oh, this is horrible. This is actually horrible. We highlight the edges between them. Not an artist. And once we have done that, we just repeat the step, unless we've found our edge, which our desired 8, which we haven't yet. So we repeat the step. We pop the last thing out of the queue. So first in, first out, that's 1. So we're going to pop 1 out of the queue. And now we're not considering 2 anymore, we're considering 1. So we pop 1 out of the queue. We are now considering node 1. Is 1 connected to anything? No, it's not. At least, well, it is connected to 2, but 2 has already been visited. And is it connected to anything unvisited? No. So much for 1. We are now done with 1, and so much for that. Now we consider node, the next one, which is 5. So we're going to remove 5 from the queue. Put it over here. 5. So is 5 connected to anything unvisited? Yes. 3 and 6. It's also connected to 2, but 2's been visited. So the way the algorithm works is we then add 3 and 6. Where's my thing? We add 3 and 6 to the queue. And we visit them. So 2, 1, 5, 3, and 6. They've all been visited. And once we've done that, we just keep going. We keep doing it. We check if we visited node 8 and we haven't yet. Just a moment. I have dinner. Dinner is good in general. Dinner is typically a good thing. Enchiladas, pretty sweet. Anyway, sorry. Distracted there. Enchiladas are cool. Yeah. Enchiladas are very cool. Very yummy. So anyway, back to it. We've got node 5, and that's the one we're considering right now. We consider the nodes adjacent to it, and we put them in the queue, and we see that they're visited. And that's it. We draw in the edges between them. Where's my brush? Here's my brush. Draw in the edges between them in green. And we have added them to visited, and we just do it again. What is first node in here in the queue? It is 3. So we remove 3, and now we're going to be considering node 3. It's my text box here. We're now considering node 3. Over here, I've just been writing whatever node we're considering at each step. So we're considering node 3, and 3 is connected to 4. It's also connected to 5, but 5's already been visited, so we just care about 4. So what we do, we visit 4, we add 4 into this line thing we're doing. We visit 4, and we put 4 in the queue. And the next thing we do is we just keep going with this. 6 is the next one up in the queue. We erase 6 over here, pop 6 out of the queue, and we put it over here. So we're now dealing with 6, and 6 is connected to 7 and 8 via direct connection, and also to 5, but 5's already been visited, so we don't really care about it. So what we're going to do is we're going to take our brush, we're going to add 7 in, we're going to add 8 in. And now at this point, and of course we would also add in 6. 6 is already in visited, but we would add in 7 and 8 to visited, and we would add 7 and 8 to the queue. But now we actually have found node 8, so we can stop here and not keep going. So we've found this green tree to be like the optimal setup, the shortest path tree from 2 to 8, or from 2 to all the nodes really. So basically 2, 5, 6, 8 is now guaranteed to be the best path to get to 8. As soon as we found 8, we just backtrack along this tree and we found the path is 2, 5, 6, 8. So if you're confused, which you probably are, oh, hey, yes, someone actually talked, but it was because of the enchiladas, but still great. So the algorithm, I should have just said this at the start, but the algorithm is this. You create a queue. It's got the star node in it and nothing else. And you also create a list called visited, which has just the first node and nothing else, because you haven't visited anything else. And now, as long as you still got stuff in the queue, what you do is you take the first node out of the queue. Remember, first in, first out, so it's the one that's been there the longest. You find all of the nodes that are adjacent to it, and you add them into the queue. And then, once you've added them into the queue, you also mark them as visited. And once you've done both add them into the queue and mark them as visited, you add the edges, connecting these new nodes to the one that you have just been considering. You add those edges to the tree, and you keep going. Once you find the end node, you stop. Or if you don't have any node, what you'll get is just like a tree. You'll be constructing a tree. If we had kept going here, this is the tree we would have ended up with. You can think for yourself about why this algorithm will never create a cycle. But basically, once we have our tree, we're very happy and we're done, because a tree is like the structure that works for shortest paths. Finding the shortest path in a tree is basically trivial. You just walk down the tree until you find the node you're looking for. Finding a shortest path in a non-tree with a lot of cycles, on the other hand, is actually quite difficult. Can it not make it a cycle because it only visits one once? Exactly. That is correct. As soon as a node is visited, you'll notice you only look at the adjacent nodes that have not yet been visited. So yes, as soon as it's been visited once, you can't visit it again. And so you'll be happy. So, breadth first search, interesting? Probably. So, that was kind of poorly explained. Are we understanding the idea? The idea is pretty central. We are basically just spreading out bit by bit, looking at the nearest ones. If they're the one we're looking for, great. If not, we just keep spreading out bit by bit. The queue is just the underlying data structure to make that work. Because if you're looking for like the nodes nearer to you, you want to be looking for the nodes that were visited last, I suppose you could say. Indeed. You will find the shortest path before you will find the cycle. Central idea of breadth first search is like, if you imagine a graph this may feel a little trippy, but if you imagine a graph as like a sequence of tubes, and you pour water into your start node, and the water spreads out through the tubes. And so it'll reach the nearest nodes, the ones that are only one edge away first, and then it'll reach the ones that are 2 away second, ones that are 3 away third. A computer can't do that all at once. It's got to do them in order, and that's why we have the queue for it. But the central idea is that you visit the nodes that are closest first, and then you visit the next ones next, and that's why the queue is there. So that first in, first out. So breadth first search, and I'm going to analyze it. Can't show that. What paradigm do we think this is going to be? Breadth first search. Which paradigm will breadth first search be? Avocado. So for those who don't remember, the paradigms are divide and conquer, backtracking, brute force, greedy algorithm, and dynamic programming, I believe, are the ones we've discussed. Yeah. Which kind of paradigm do you think it would be? This is kind of a trick question because breadth first search doesn't really have a paradigm. It doesn't really have a paradigm of its own, but because it's not really optimization. But if it were to have a paradigm, it's usually considered to be greedy because it takes the nearest things first, and it just makes these small, low-tier optimal decisions, and overall that adds up to an overall optimal outcome. So it's taking the nearest ones, and because of that, it's greedy. Because like, if you imagine a person who just grabs the thing nearest to them at all times, they're a pretty greedy person. So yeah, that's why it's a greedy algorithm. And as for the big O is the number of nodes plus the number of edges. It'll take if you give a graph to the breadth first search and say, hey, I want you to find the tree in this graph that has all the shortest paths in it, then and this graph has about n nodes and about e edges, then it'll take roughly n plus e steps. And the reason why is because it visits each edge roughly once, and it visits each node roughly once. And the paradigm is greedy. So yeah, this explanation might have been poor, but the central idea is just you're spreading out bit by bit. You find all the ones that are 1 away, then you find all the ones that are 2 away, and you find all the ones that are 3 away, and you just keep going until you found it. So, however, this is not a very good model of the real world because like travel time matters. If I gave you 2 flight routes and between say Auckland and Christchurch, and one of them goes from Auckland to Christchurch like a normal person, and the other one goes from Auckland to Christchurch, but it goes like out all the way over to the North Pole, and then it comes all the way back down to the Southern Hemisphere and gets to Christchurch. Like, you probably want the shorter one because time matters. We're busy people. We can't be going up to the North Pole on random getting excursions, even if we're not landing at any airports. It still takes time. So the way that we work this into our model of graphs, we add weight to the edges. Ignore the arrows. The arrows don't matter. What does matter is these little numbers beside these edges in this graph that's been drawn here. These little numbers signify the weight. So the weight of the edge between A and C is 12. Weight is very important because, I mean, let's look at our examples of graphs. In the house layout one, distances between different rooms is somewhat of a factor, and those could be the weights. In the friendship one, the strength of a friendship could be the weight. For example, if you got a good friend, he might be a 1.0, but then if you got a bad friend, they might be only a 0.3 or something like that. Computer systems is a very central one. 2 computers might be talking to each other, trying to exchange bits of information, but their connection is like really tenuous. Maybe someone's microwaving nachos in the middle, so like it's a poor connection. But on the other hand, if there's no microwave nachos in the middle, it might be a stronger connection. Yeah. So in any case, this is what we do. We add little weights to the edges, and what we have now is what's called a weighted graph. And breadth first search doesn't work in weighted graphs because breadth first search is a greedy algorithm. And if you remember back to the crab cake example all the way back in session 2, greedy algorithms don't tend to work too well when there are like consequences further down the line. In the crab cake example, we had like a graph. Alt escape. We can now model the crab cake example much more efficiently as a graph. Where's my thing? The crab cake example was, don't save, was where we had like the start, and then we had good crab cakes, and then over here we had bad crab cakes. And past here we had just like a road. whereas past here we had like Hell itself, and then here is the destination. Aye. So where's my lines? Here we go. So the graph is like this. You start at the start node, you end at the destination node, and you're trying, and in this case, there would be weights on the edges. So the weight here would be like, oh, bad crab cakes, so 0. We don't like bad crab cakes, whereas this is maybe +10. We love good crab cakes. And hell itself is like -100, -1,000, whatever. And this doesn't really matter. This is just road, but you have to pass through hell itself. So to pass along this stretch of road, it's going to be -1,000, whereas this is just going to be 0. So this distance here has a total sum of goodness or badness being 0, whereas this one here is -990. So the breadth first search algorithm would go along. Wait a minute, actually, it would go along either route. Give me a second. Erase. If we imagine, not sure why I erased that, but if we imagine like there's an extra stop in the middle here, instead of just being a normal road, there's like an extra stop along the middle, then the breadth first search algorithm would say that this is the optimal path from start to good crab cakes to hell itself to destination, because that's only 2 stops along the way, whereas start to bad crab cakes to road to this extra stop up here to destination is 3 stops, and that's longer. But of course, the second route is better, because you don't want to go to hell. In general. Bad crab cakes be -5. Okay, it would probably be -5, but it wouldn't be as bad as hell itself, is what I'm trying to say. And that's why breadth first search doesn't work in this case, unfortunately. So much for that. Back to this. We add weight to the edges, and that makes our algorithms work better. So if breadth first search doesn't work, the question is, what does work? How can we find the shortest paths in weighted graphs? For example, in this weighted graph, if you wanted to go from E to C, you would go E to A, 7, and then A to C, 12. It's probably the best option. What if this edge here had only a weight of 1? Then you could go E to A, 7, A to B, 10, B to C, 1, and that's actually less because A to B is 10, B to C is 1, that's a sum of 11, and that's better than the 12 here. So if you want to minimize the total sum, I should have made that clear by the way, we want to minimize the total sum in this case, then EABC could be better in that case if this 20 was replaced by a 1, and EAC is the best here otherwise. So to find the optimal path in a weighted graph, we're not going to deal with that unless we have time, and we probably won't. But it's called Dijkstra's algorithm. I'm thinking of doing it in the next session. In any case, there's something more interesting, and probably a little easier to understand, and that is a minimum spanning tree. So first up, let's talk about what a spanning tree is. Alt-Tab. No, I said Alt-Tab. I said Alt-Tab. File, new file. So a minimum spanning tree is when you've got like a lot of nodes in a graph, and some of them are connected and some of them ain't. Say A, this takes a while, but please bear with. It's going to draw a lot of letters all over the page. Great, tremendous fun. We're having so much fun, and we're going to draw in some edges as well. Yeah, A, B, C. Maybe add it to E. We add that to G. Maybe connect F to G as we can. This to A. And just a bunch of edges. A lot of edges will make this good. So a spanning tree, and notice by the way that there are cycles here. This is very much not a tree graph. For example, CAEB is a cycle. CADC is another cycle. You can go around and around and around them. Okay. Leave a little early today. That's fine. Have a nice day, boss. In such a graph as this, we could create what's called a spanning tree, which is a tree which is composed of some of the edges, but not all of them. If it was composed of all the edges, it wouldn't be a tree, but does contain all the nodes. So to see what I mean, we could take, for example, let me have my brush, and I'm going to color in the spanning tree red and get the biggest size. So for example, we could have this as a spanning tree. We're going to add in this, 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 and this edge. That last one was rather poor. And this edge here. And this is a spanning tree because every single node is involved, but not every edge is necessarily involved. And so what it is it's a tree. There's no cycles here. Sorry for the drawing that the DA edge crosses the FG edge, but yeah, there's no cycle there. And yeah, it's a tree within a graph. So are we comfortable with this idea that we can have like a tree as a kind of subgraph of a graph, kind of smaller part of the graph, which is composed of just some of the edges, but all of the nodes? Yes, sir. Jolly good. Everyone else comfortable with it? We got thumbs up, thumbs down, stuff like that. Anyone want me to go over it in more detail? Because it is a somewhat pernicious concept. It seems immediately easy to some people and not so immediately easy to others. But if no one has any problems, we can now deal with the idea of what if these edges had weights? I'm not going to draw on all the weights because that would take too long and try your patience even more. But what if all the edges had numbers on them? I mean, we can draw a lot of different minimum spanning trees. I mean, just normal spanning trees. We can draw a lot of different spanning trees. For example, we could also try this one, which contains this edge, this edge, this edge, this edge, this edge up here, and this edge up here. This is another perfectly valid spanning tree, which almost threw me for a loop there because I thought that this was a cycle, but no, it is not. This is a perfectly valid tree with DA, AC, AE, CB, EG, and GF being the edges. There's no cycles there, and it's a tree. It contains all the nodes, A through G. We're happy. But these are two very different trees. And what if there were edge weights here? What if we want to find, among all these different possible spanning trees, which we could possibly make, what if we wanted to find the one that was smallest in terms of edge weight? For example, there are real-world contexts in which you would want to do this. I will get this to go away. The real-world context in which you would want to do this. For example, if you wanted to hook up all of the houses in a town to an electrical grid, and this was where this problem first came up in Mikulov in Moravia, where they wanted to do exactly this. They wanted to say, hey, it's the turn of the century. We need electricity now. We need automated bathtubs, or I don't know what they needed in Moravia in like the middle 90s, but whatever. They were hooking it all up to electricity, and they needed to basically have every town needed to be on electricity. And they would string wires under the roads between house to house. Every house needed to be on electricity. So this is a spanning tree. What we need is a spanning tree. We need all of the nodes, but only some of the edges. We're not just going to draw all of the different connections in with wire and run electricity through all of it, because that would waste a lot of wire. What we need is a spanning tree, and not just any spanning tree, but the minimum spanning tree, because the government didn't want to fork out a lot of money to pay for the electricity bills of all of their constituents. They just wanted to spend some money on the copper wire, because copper wire is expensive. So if you imagine that all of these little nodes are houses in Moravia, in Mikulov, and all of the edges symbolize possible cabling places, and the numbers on them, the weights, symbolize like how much it would cost you to do those possible cabling places, then you'll find that what we've bolded in here, this selection of edges, is the minimum possible spanning tree. It's a spanning tree, it has all of the nodes in it, and it has the smallest possible edge weight. If you drew another spanning tree, I guarantee you it would have higher edge weight in total if you summed up all of the different edges over all of the nodes, over all of the edges involved in your spanning tree. So here that would be 2 plus 2 plus 3 plus 8 plus 8 plus 7 plus 4 plus 1 plus 3. And you'll notice that we've avoided like the 10 and the 18 and the 9 here. We've gone for like the smallest possible overall sum. That's what's called a minimum spanning tree. Now, a quick question. How could we make a minimum spanning tree? If I gave you a graph with weights and I asked you to make the minimum spanning tree, how could you do that? Does anyone have any ideas? And me asking this question is most certainly a proxy for me to eat a bite of enchilada. Excellent. So we have two people who both have great ideas, and in fact, they have the same idea. And that's because it's a good idea. However, there are a lot of possible minimum spanning trees. And just out of curiosity, who can tell me what's the paradigm that those two answers from Caroline and Jessica, what could tell me Who could tell me? Not what could tell me. I'm speaking too fast for my own good. Who could tell me what paradigm that is? It's not greedy, no. It's not greedy. It is not dynamic programming either. It is the least fancy of the methods. It is brute force, where we look at every single possible combination and just check which the best one is. Straight up brute force. Yeah, it's one that's often overlooked. However, there is actually a greedy solution to this problem, and it's called Prim's algorithm. Picture it as a primrose, which is a cool flower. Yeah, skull emoji. Good fun. Don't die. Prim's algorithm is not anything to do with flowers. It's to do with making a minimum spanning tree in a given graph. And so here's how it works, and it's reasonably simpler to understand, much simpler than breadth first search. So the way it works is I'm going to have to actually get myself a tree here, aren't I? What a shame. What a shame. I'm going to take this tree and put it in, once I can figure out how to do this. Copy this. Hopefully this works, otherwise I'll just look pretty stupid. File, new, and save. Doesn't work. Damn it. Okay, this is called improvisation. You'll notice that I took my thing from the first result on Google, and that is because I'm shamelessly bad at creativity. So we're going to save image as minimumspanningtree.svg, and we're going to open a new paint thing. We're going to file, open minimumspanningtree.svg, which should be somewhere in downloads. It's not. Why is this not in downloads? Paint. Yes, here we go. Okay, it all worked out in the end. So we've got our minimum spanning tree. We're going to zoom out a little, zoom back in a little, zoom back out a little. Okay, this is well done for. There we go. Nice. Nice zoom level. So we've got our tree. And if we just ignore the bolded stuff already, what we're going to be trying to do is construct a minimum spanning tree and show how Prim's algorithm works. So the way it works is first up, we just pick any node at all. So for example, we're going to pick this node to start because this is a reasonable node. Oh, well, get the size right. This is a reasonable node. We're going to pick this node to start here. Now, the way Prim's algorithm works is first, you select the smallest possible edge coming out of the subgraph, which we've colored green, into the rest of the graph. So in this case, we've got a 9, an 8, and an 18. So the 8 is best, and we add it to the tree. It's horrible, but the 8 is best, and we add it to the tree. And therefore, we also add the node at the end of it. Now we select of all the edges coming out of this graph to the rest of the graph, which one is smallest? Because here we've got an 18, a 9, a 9, a 9, an 8, a 7, a 9, a 10. And those are all the edges coming out. This is greedy. Yes, this is exactly greedy. Prim's algorithm is a greedy algorithm. Congratulations. Yes, I was just about to ask the question, but yes, it is a greedy algorithm. And in this case, 7 is the greediest of the greediest edge, like the smallest one. So we go with 7 and we connect to here. Now we're at, we've got a bigger graph, so now we need to consider all the edges again. We've got a 9, a 9, a 9, an 8. We've got 7 already, sorry. A 9, a 9, 4, a 5, a 9, a 10, and an 18. And of course, the smallest one here is the 4, so we're just going to connect up that 4. Nice and easy. And add this node in. And now, I think you can probably guess where we're going with this one. 18 is the best when it comes to if we wanted to find the maximum spanning tree, but we're trying to find the minimum. And now, who can tell me what the weight is of the graph of the edge that we're going to add next? Who can tell me? Oh, it's 7:52. Time flies away from you. Yes, 1 is correct. This is the smallest one, 1. You'll notice it's actually the smallest in the whole graph, so it's not too big of a question. If it's the smallest in the whole graph, it certainly is going to be the smallest that we've got on offer, so we add it in. And now, who can tell me about the next one? Because we've got 5, 9. Actually, no, we don't have 5. Here's an important thing about Prim's algorithm. You're only taking edges between the green and the not green. So 5 is not allowed because that's between 2 green nodes. But 3, 9, 9, 8, 9, 9, 9, and 18 are still available. And of course, we pick 3. Yeah, it's the smallest. And now we keep going. And now of all the things, 9, 9, 9, 18, 18 is no longer available. We've got both of the endpoints. We've got this one and this one, which are the endpoints of the 18. So 18 is no longer available anymore. And it looks like 18 is just never going to join the tree, shockingly. Who would have thought that the biggest edge is not going to be in the minimum spanning tree? But anyway, the smallest one is now 8. Of all the ones we have on offer, it's 8. We're going to stick it in. And now we've got 2 2s. And here we just do either. We legit just do either. I know. It's a shame. 18 is the best. And we got 2. And so we're just going to do either. We're going to put it in. And now we've got 6, 4, 9. No, we don't have 9. Sorry. We don't have 9. Keep getting tripped out of that. 9 is between 2 green nodes. We don't have 9. We've got 6, 4, 2, 9, this 9, and this 9. Which one is the best there? Well, it's not a difficult question, it's 2. And now, since we've only got 1 step left, I'm going to ask a capable person in the chat, preferably someone who hasn't talked already, to tell me all of the different edge weights that we have on offer here today. Like all of them. That the weights of all of the different edges that we have available, because there actually aren't that many right now. Yes, not you, because you have talked so much, and that is very good, and I'm so happy that someone is really into this. Yeah, you might have a job in programming somewhere ahead of you, but someone who is not you, what are all of the edges we might be considering right now? We're going to be taking the minimum one of them, because this is a greedy algorithm, but who can tell me all of the different edges? PR is a good field. Anyone got any ideas? Okay, Victor, that is a very well done, but unfortunately, you have missed one of them. So 4 here is between 2 green nodes, so it is disallowed in this case. However, 3 is correct because it's between a green node and a not green node. And 9 is correct because it's between a green node and a not green node. I'm going to highlight in red the ones that Hector has said. Highlight in red the ones that Hector has said. That works out very nicely. That's a rhyme. Hector has said 3 and 9, which is correct, but unfortunately 4 is between 2. Yes, why are you only talking about the enchilada, people? Come on, come on. I need your help here. So there is one other who can spot the weight of the last edge between green and... Damn it, man. Damn it. Okay, we got our answer. No, it's fine, it's fine. So these are our available remaining edges. 3, 6, and 9. And of course, 3 is the best. So of course, we're going to take our green. We're going to slap it on the 3. And would you look at that? It is peculiar. If I get rid of all this color that I've drawn on, I know, a lot of work being undone, you'll notice that I've literally just colored in what they said was the minimum spanning tree. And that's because Prim's algorithm works. Surprise, surprise, people. Surprise, surprise, Prim's algorithm actually works as an algorithm. So, anyway, we are on Prim's algorithm, and it is a greedy algorithm. More interesting is its big O notation. Who can tell me why it might be OV squared, where V is the number of vertices? Oh, sorry. Nodes are often called vertices in some literature. I should tell you about that. If you ever look into graph theory, you'll find them being called vertices often. The words are the same. They're interchangeable. You might even find them being called points in really old textbooks. So who can tell me why, if we had, say, in nodes, who can tell me why it's going to be O(n) squared algorithm? Yes. Where's my screen sharing? Chat, whatever it may be. It's a difficult question. And I will not be surprised if no one answers it, because it is a very difficult question. What's this down here? Minimum spanning tree. Get, don't save. Man, this is broken. Zoom is for some reason breaking my computer. Can't tell what the time is. I'll just ask Google, what is the time? Please, Google, tell me. 7:58. We might actually finish on time this time. This is so great. So the reason why Prim's algorithm is O(n) squared is because, and by the way, we are not going to do the time permitting thing, but this fellow here, Edgar Dijkstra, is the originator of this very complicated algorithm. It's actually not as complicated as it looks, and we will cover next session. So the reason why it is O(n) squared is because at each step, Prim's algorithm is going to be looking at all of the edges between the subgraph and the outer graph. And so that's going to be at most in edges, because it's going to be, well, no, that's not true. It's going to be like, overall, it's going to be on average in edges, because at the end of the procedure, there's only going to be like 3 edges. Remember, we had only 3, 6, and 9, and at the start, you might have a lot of edges. Well, actually, at the start, you'll only have few edges, and then somewhere in the middle, you'll have a lot of edges between the green subgraph and the non-green subgraph, and then the number of edges between green and non-green will keep decreasing. It'll increase and then it'll decrease, and overall, it'll be in on average, where in is the number of nodes. And of course, you're going to be doing in steps, right? Because at each step, you add another node in, and you got to add in all in nodes over all the time. So you're going to have to do in steps exactly. And so it's going to be in steps, and in each step, we're doing in operations. We're trying to find like this in each step. In fact, if I still have algorithms 3, in each step, we're going to be doing a linear search to try to find our desired smallest one. So for example, among 3, 6, and 9, any sane human is like, oh, 3 is the smallest, but a computer actually needs to find it. And so a computer will linear search through 3, 6, and 9 and find 3 is the smallest, and that'll be O(n) time. And then if we're doing O(n) time in times, that'll be O(n) times in, which is O(n) squared. Kind of playing it fast and loose with the big O notation here, but that is essentially why it is O(n) squared. You're doing in operations, and you're doing in operations each time. And I'm from America, and you're doing it in times. In operations each step, and you're doing in steps. So it's going to be in squared operations total on average, excluding constants, of course. So, as far as I can tell, that is actually all. And that is a great day.